Hey guys, welcome back. So today's Tuesday and we're going to be talking today about how we take a word equation and we move it into a formula equation using formulas and symbols to complete the reaction. So on Monday, we talked a lot about having a sentence, okay? So an equation's written out in a sentence form. And how do we take that sentence form and move it into a word equation where we're just taking like the reacts with and changing that to a plus sign and the word to form and we're changing that into an arrow. So now we're going to be moving into what causes reactions and then taking these reactions and moving them into a word equation in which we use formulas and then we use symbols to identify whether it's a solid, liquid, gas, or aqueous solution. We talked a little bit about those symbols on Monday as well. So the first thing I want to talk a little bit about is what is reaction energy. So when you have a chemical reaction, you have a certain amount of energy that occurs while the reaction is taking place. Now, sometimes when you're mixing these reactants together, you mix them and poof, it just happens immediately. You've got the reactions already going and it's going to go to completion. Then there's other times where the reaction's kind of just sitting there and you're like, okay, why is this not reacting? Well, sometimes you have to activate that reaction. So we call that activation energy. And sometimes we have to use heat to do that. Sometimes we have to use a catalyst, which we talked a little bit about at the end of our notes on Monday. So when we're talking about a spontaneous reaction, okay, they proceed immediately. So think about the video I showed you on Monday at the end of our Google Meet. You saw the fire, right? The big fireball that was in slow motion. That's a spontaneous reaction. So immediately when I mix those reactants together, they would react with one another. Now I did add some energy. I did add some fire to that, okay? But a lot of times, some reactions take a long time to occur. It's kind of like when you get up in the morning and you're like, oh, the alarm has rung already and I'm trying to get up. Well, that's kind of what happens when you're trying to use activation energy. So, if you're using a catalyst, right? It's the amount of energy that's required to start a chemical reaction. So think about if I put two chemicals in a test tube and they're just sitting there, okay? They're not going to do anything, right? But once I add that Bunsen burner, I add that heat there, that energy, it's going to start going, and then the energy is going to take hold, and then the reaction's going to proceed until all of the reactants are used up and the reaction stops, okay? Now, there is a process of how a reaction keeps going and how it stops. Now, when you do that, we're going to talk a little bit about that probably when we get to stoichiometry, when we talk about limiting and excess reagents, but we're not only going to focus on that in this chapter, okay? So that's spontaneous and activation energy. Now we're going to talk a little bit about our formula equations, okay? So formula equation, it uses formulas and symbols to describe a reaction. It doesn't indicate how many. We'll talk about that later when we balance reactions. And then all the chemical equations are sentences that describe reactions, okay? Now, we're going to talk a little bit about diatomic elements, excuse me. We talked a little bit about this in the covalent chapter when we were doing bonding. Diatomic elements are those elements that when they exist in nature, they cannot exist as singular elements, okay? So oxygen, fluorine. So it actually makes an upside down L on the periodic table, starting at nitrogen, going to fluorine, and straight down. These elements are very reactive with the elements around them. So when they exist in nature, naturally, they have to exist as a molecule. They cannot exist as a singular element. Now you ask, why is that important to know for chemistry? Well, when we start building these formula equations, and I say, I'm going to react hydrogen with oxygen to form water, you need to understand when you're building the formula equation that hydrogen is not just H, okay? Because hydrogen can't exist in nature singularly. It has to exist as a diatomic molecule. So when I write that formula for hydrogen, I'm going to write it as H2. When I write that formula for oxygen, I'm going to write that as O2. Now, that doesn't affect the fact that when you mix them together, you still make water, okay? We'll talk a little bit about that later when we start balancing equations, okay? That's where that comes into play. But diatomic molecules, they cannot exist as singular elements. So we often use that term Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, Brinkel-Hoff. That's kind of a shortcut way of learning the diatomic molecules, okay? Now, they also, most of them are in the same column, 1 and 7, but you got a couple, you got 1 in 15 and 1 in 16 as well, okay? Now, these are the diatomic elements, and this is where they're located on the periodic table. Like I said before, you can tell that it makes an upside down L right there. Those are your diatomic molecules. Okay, now, this is where we're going to show you how to do the conversion. First thing I want to show you is this is what you learned on Monday, where I gave you a sentence form, right? Solid iron 3 sulfide reacts with gaseous hydrogen chloride to form iron 2 chloride and hydrogen sulfide gas. That's what you did on Monday. Now, Monday you took that word that sentence and transferred it into a word equation, which is what you see here. So now I took this sentence and I said, okay, I have iron 3 sulfide plus, because that's your reacts with hydrogen chloride, right? To form. To form is your arrow. Iron 2 chloride. And remember, and is also another way of saying a plus sign, plus hydrogen sulfide. So that is your word equation. That's what we did on Monday. Now we're going to take this word equation and build a formula. So this is where you're going to have to use that periodic table. Now I've given you some things in the slideshow. I told you these are resource materials, okay? These resource materials will be very beneficial for you when you're doing this chapter, okay? So you'll need to use those resource materials. Now, so if I look at iron 3 sulfide, so iron 3 is telling me that it's a Fe plus 3. Sulfide is a minus 2. So when I put them together, it's going to be Fe2S3, okay? Plus, and let me just go ahead and give you the equation so you understand what I'm talking about. Okay? So because iron 3 is a plus 3 and sulfide is a minus 2, when it forms, remember, if they don't cancel, they crisscross. So it becomes Fe2S3. Okay? Now you have hydrogen chloride. Hydrogen's a plus 1, chloride is a minus 1. They cancel, so you end up with HCl. Put your arrow in. Now we have iron 2 chloride. Iron 2 is a plus 2. Chloride is a minus 1. So a plus 2 and a minus 1, they don't cancel, so you crisscross. And you write FeCl2. Plus hydrogen sulfide. Hydrogen's a plus 1. Sulfide is a negative 2. They don't cancel, so you crisscross. So it becomes H2S. So this is how you build the formula equation from the word equation. Okay, this is going to take you a little more time to do. All right, so let's do another example. So here we have our sentence equation. You have nitric acid dissolved in water reacts with solid sodium carbonate to form liquid water and carbon dioxide gas and sodium nitrate dissolved in water. Whew, that's a lot to say, isn't it? So I'm going to take this and transfer it into the word equation, right? So we have nitric acid plus, because it says reacts with, so there's your plus, okay? And somehow I missed this, so I'm actually probably going to have to rewrite this for you on the board here in a minute. So it actually should have been nitric acid plus sodium carbonate, okay, plus water and carbon dioxide and sodium nitrate. So disregard the formula I did there, and let's just go ahead and look at the bottom part. All right, so this is what it should have said. Nitric acid plus sodium carbonate yields sodium nitrate plus water. And then I think I missed carbon dioxide gas in that too. So I kind of messed up that equation, but there you see, Miss Urshery does make mistakes. So that was kind of a disheveled slide there. Now, what I'm also going to do is I'm going to show you in another video, I'm going to do a sample video, and I'm going to show you how to do some of these problems in using my my little document cam, where I'm going to write these out just to kind of give you extra practice before you start your worksheet, because you're going to need some extra examples. And that one that I just did was not a very good example. So I want you to be able to work these out and do these formula equations. So I'm probably going to demonstrate about 5 of those. Please make sure you look at that and don't just jump right into the worksheet and start it, okay? This extra ancillary video will help you get started on that worksheet. So it's going to take you a little bit to do that worksheet because you're going to have to start using the formulas and the ions and things like that. Please just don't look up the formulas on Google and just write them in there, okay? Because it's going to be a lot harder when you take a timed test if you guys don't know how to actually do these reactions, all right? So wait for the next video, watch that before you move on to the worksheet. It will help you, I promise, okay? I hope you guys have a great day.